We live in a world where computers can see, hear, and talk, tasks that are very simple for humans. But it took us few decades to enable machines to do so, thanks to a set of advanced artificial intelligence algorithms called deep learning. Deep learning is not new. In fact, their initial concepts were introduced decades ago. But we finally managed to refine them and run them in large scale because now we have the data and computing power that deep learning needs. My name is Dr. Reza Shahamidi, and I'm a deep learning software engineer and researcher. In this lecture, I'll explain what deep learning is, how it biologically inspired, and what we can and can't do with it. This is not a technical lecture, as I don't teach you how to implement these algorithms. It's only an introduction for those of you interested to know what we mean by the term deep learning. Without any further ado, let's get started. Before we start talking about deep learning, it's better to just understand what's the difference between traditional software programming and basically machine learning software, or software that is called machine learning. With traditional software, we have a set of rules and some data. And we basically know how we want to apply those rules on the data to reshape that data to produce some outcomes or answer some questions, etc. So our job as software engineer is to implement those rules that are able to process this data in order to produce this answer. The key thing here is we know what we want our software to do with the data to transform it. Then we implement it with a series of coding solutions that we have, or coding commands that we have, like conditional statement, loops, and etc., in order to perform or implement those transformational rules. However, there are some situations that we don't know those rules. For example, assume that you want to code a software to produce a speech. We don't know how we can take an input signal, or a text in this case, and program a software to produce that speech. Or it would be extremely complicated to implement those rules into a traditional software. That's the case where machine learning comes into place. With machine learning, we have the data and we have the outcomes, or the results of presenting that data to the machine, to the software in this case. And the machine learning is capable of understanding and learning what a transformation of the data is required to apply in order to convert or transform that data to those answers. So with machine learning, we don't know the rules, or we don't know how we want to transform the data, but we have observations of our data samples. That means the data, the input data, and, for example, the outcome or the answers that the system is expected to produce when that data is being given. And then through a learning mechanism, machine learning figures out those rules using that learning procedure. So machine learning algorithms are trained rather than explicitly programmed. If you know how to transform your data, if you know the rules that your software needs to implement, and you can do that, we don't use machine learning. Instead of that, we use traditional software. Before we talk about deep learning and deep neural networks, it helps us to understand how biological neuron works and their structure. What you see on the screen is a biological neuron. It's composed of three components: axon, the neuron itself, and dendrites. We can see biological neuron as a very small computing unit with input, processor, and output. So the axon acts as the receiver of the electrical signal when the neuron performs the processing of that signal, and then it sends or broadcasts the results to the other neurons connected to it via its dendrites. However, not all the time the processing of the neuron results in the broadcasting of the results or the output to the other neurons via its dendrite. What happens is the processing that the neuron performs of the signal should meet a threshold that basically activates the neuron to send and broadcast the data or the signal to the other neurons that are connected to this particular neuron. And that's basically how billions of neurons in our body operate and communicate and process and enable us to think, learn, and sense. If we think of each biological neuron as a very small computing unit, then having more of those computing units means that we are more intelligent. That means we are capable of processing and learning and memorizing more information. So it would be a good idea to have some comparison of between different species in terms of the number of neurons. For example, a sponge has 0 neurons, so it basically has no capability to learn anything, no intelligence whatsoever in a sponge. A jellyfish has 5,600 neurons. A frog, 16 million neurons. A dog, 2.2 billion neurons. Obviously, a dog is way smarter than a frog. A gorilla, 33 billion neurons. Humans, around 86 billion neurons. So you may ask that we should have the highest number of neurons among other live beings. In fact, that's not the case. For example, an African elephant has around 257 billion neurons, which is 3 times of a human. However, the number of neurons in our brain and our neural system in compare to our size makes us the most intelligent on Earth. Now that we have some understanding of a biological neuron, let's define an artificial neuron. So these are the inputs to the neuron. The neuron itself, that is the CPU of the neuron type of thing. And finally, the outcome or the output of the neuron that is similar to the dendrite, and we can have multiple of these outputs. When you're dealing with machine learning algorithms and basically terminology, the concept of independent variables and dependent variables, it is something that we basically call instead of inputs and outputs in many occasions. So independent variables are the inputs to your machine learning algorithm, and dependent variable is what your machine learning is expected to produce in basically your system. So in this case, for example, we have x1, x2, and xn, and these are the inputs, and y is our output. For each of these inputs, an artificial neuron also adds a weight. And so we have this weight 1 or W1 associated with x1, W2 associated with x2, and as many inputs that we have. The job of the neuron itself, the processing that it performs, is actually a very simple summation, and that is the summation of the value of the input signal times its weight. And then that value is sent to the output. But remember, we discussed that with a biological neuron, not always a signal or the results of the neuron processing is broadcasted to the other connected neurons. The neuron needs to get activated in order to send that basically signal. So that's what this third steps comes into place, where we have something called an activation function, and its job is basically to squash the value of the output of the neuron between certain values. Among popular activation functions are sigmoid, tangent, hyperbolic, ReLU. So, for example, sigmoid squashes any value between 0 and 1. Tangent hyperbolic squashes any value between positive 1 and negative 1. ReLU doesn't get activated for any negative value. So the output of ReLU is 0 for any negative value. For any positive value, that value that directly goes to output. And then we have leaky ReLU that considers a small negative basically outcome if the result is negative as well. Among these four activation functions, sigmoid and ReLU are the most widely used activation functions, although we have more activation functions in addition to these four shown here. In addition to weights that are associated to each of these inputs, each neuron has another parameter called bias. In fact, the training process is the process that these weights for each of these inputs and the bias is basically calculated. So we call these weights and the bias trainable parameters. During the training process of your machine learning algorithm, of your neural network, these weights and biases gets adjusted. And finally, the outcome of your neuron becomes applying the activation function that you select to the result of this sigma operation. Now we are in a place to define deep learning. So far, we talked a little bit about machine learning in general, about biological neurons, and about the structure of an artificial neuron. Deep learning is the umbrella term that we use for a set of algorithms that basically try to mimic human thinking and learning process. And they all use these artificial neurons that I just show you. This is a very small computing unit that all they do is to calculate that total sum of their input values, their weights, and the bias, and then apply the calculation function. So because they are based on artificial neural networks or artificial neurons, we call them biologically inspired. But they are actually a mathematical framework for learning representations from data. A deep net or a deep neural network is a combination of these sequential layers, and each layer tries to understand or tries to learn a different representation of the data by mining intelligence from those training data, which is basically samples of inputs and their associated output that we provide via training. Note that deep learning is not a model of biological brain. The reason for that, we actually don't know how brain learns, so we can't say that deep nets are models of our brain. Over the past few years, deep nets have proven to be more effective than traditional machine learning algorithms that we sometimes call them shallow learning. With the deep net, multiple representation of the data can be created automatically, and that so that because it's automated, we can have as many of these representations as we need. However, with shallow learning, each of those representations may require to be manually engineered. That makes it very complicated to have these different representations of our data. For the past few years, deep nets have won the majority of machine learning competitions across the globe, and they have been one of the most on-demand research topics in automation, intelligence, and robotics. They are specifically very powerful with processing and learning intelligence from unstructured data and multimedia data like audio, like video, like text, etc. Imagine that you have two sheets of colored paper crumbled together. Each of those sheets is a representation of a class of data. For example, suppose that each class of that data is one class of data is dogs and one class of data is cats, and you're trying to design an intelligent computer vision algorithm that can look at a picture of dogs and cats and says whether it's cats or, for example, or dogs in that picture. What DNN does, it finds a transformation of that crumpled ball into the sheets of the paper. And in order to do that, it basically applies an incremental process of learning and experimenting to basically find a way to uncrumple that ball of papers. Now, let's talk about some common terminologies in machine learning. First of all, we have three generic classes of machine learning algorithms based on the way that we want to present the data, whether we have basically labeled data, whether we have observations or not. The first one is supervised learning. Assume that you want to train your kid or your younger brother to basically discriminate between dogs and cats. So you show your brother a picture of a cat and then tell your brother, hey, that's a cat. You show him a dog and then you say, hey, that's a dog. And then eventually via practice and providing more examples, your younger brother or your children learn to basically identify cats from dogs. So with supervised learning, our training data has their associations with it. That means we know that sets of input that we give our model, that we give our AI, belongs to that specific class of data. For example, we know that picture is a picture of cat. We know that picture is a picture of dog. In that case, we have supervised learning. And we have different type of tasks in supervised learning, like, for example, classification, regression, object detection, etc. In contrast to that, we have unsupervised learning. That means we have data samples, what we don't know basically which class though that data sample actually belongs. Assume that you have a photograph of multiple people, but we actually don't know who those people are in that photo frame. In that case, we have an unsupervised learning when the data that we have are unlabeled. An example of those unsupervised learning tasks is clustering, where the algorithm tries to find similarity between different observations of your data and put them into different clusters based on those similarities. Another type of classification algorithms are reinforcement learning. And this time we have a robot or an AI agent, and what it wants to do is to find or to understand a set of rules by trial and error. For example, you can design reinforcement learning to play a game and learn the rules of that game on itself. At the time of this recording, supervised learning algorithms are the most widely used algorithms. With unsupervised learning and reinforcement learning, they are more in research areas, although new applications on supervised learning and reinforcement learning coming out every day. In terms of the tasks that we can perform, we have binary classification, multi-class classification, multi-label classification, scalar regression, and vector regression. With binary classification, you're training a machine learning model to identify between two classes. Our cat and dog example, a machine learning algorithm that can classify a photo of a cat or dog, we can say it's binary classification. With multi-class classification, we have more than two classes of data. Or, for example, handwriting recognition or digit handwriting recognition, we have 10 digits. That means we have 10 classes of data. Then we have multi-label classification. That's when an observation can belong to two or more classes of data. For example, in a set of only cat and dog, you have more classes of animals, and you have photos that they have both cat and dog in them. So you want to classify and associate them to both cat and dog classes. With a scalar regression, the outcome of your model is not a class. Instead, it's just a continuous number. For example, predicting house prices. Let's say you have a bunch of indicators like the location of the house, the year it's been built, the dimension of the house, the number of bedroom, etc. And you want to train a machine learning model that can predict the house price based on those indicators. And that house price can be any number. With vector regression, we have multiple scalar regressors. Now let's talk about the common supervised deep neural networks. The first one is dense, or sometimes we call it fully connected neural network. With a dense neural network, we have a combination of these layers. We have the combination of neurons, and we put each of its sets of neurons in a layer, and each of those layers provides a representation of the data, and that representation, as I explained, is learned via the training process by processing and mining the samples of your input and outputs. So we start with the input layer. That's where all your inputs basically connected. The number of layers, the number of neurons that you put inside your input layer equals the number of indicators you have. For example, in the house pricing, suppose that we have 4 indicators: the size of the house, the year the house was built, the condition of the house, for example, how many bedrooms, for example, the house has. Each of these are an indicator, and we need to assign one neuron for each of these indicators in our big nets. And then in between, we have a combination of hidden layers. How do we come up with this combination is based on experience and based on how much data we have, the complexity of the data. It's a trial and error process to come up what goes between your input layer and your output layer. And the output layer is, again, composed of multiple output neurons. Each of those output neurons associates to a class of basically your problem. For example, if we have a binary situation, we can have only one output layer or even two output layers, depends on what we try to achieve, etc. Then we have convolutional neural networks, or simply convnets, and they are the primary algorithm that we use when the input to our neural network is an image. So they are very good for computer vision. They're very good for understanding what the image, for example, present, what's inside the image, or even video processing as well. The input to convolutional neural network is basically a matrix. Uh, that matrix has the size of the matrix is based on the size of your the dimension of your image, how many pixel it has in each row, and how many pixel it has in each basically column. If the image is black and white, we have only one dimensional matrix. If the image is color, we have more than one dimensional image, dimensional matrix. For example, for an RGB image, we have three of these basically matrix. Each matrix provides the value of that pixel in respect to that, for example, color. These input images are usually fed to a set of convolutional layers. This convolutional layer, they try to basically represent the image in different way and try to highlight different sections of that image that has a specific meaning for them. And then we have a set of pooling layers, and their job is to basically extract the important information of that convolutional setup. Sometimes there is no dense neurons or a typical DNN attached to this connet. Sometimes there are, for example, in here, the outcome of these feature representations are given to dense, fully connected neurons. So back to our cat and dog example. Suppose the input to your ConvNet is this image of cat, and you want to basically ask this question that, hey, CNN, is this image belong to a cat or a dog? The way that convolutional layers basically work is they try to apply different transformation of that image in order to extract specific features. For example, this convnet layer acts as an edge detector. Another layer acts as a bright light or bright green dot detector, act as an eye detector to recognize the features of a cat eye from a dog eye. And together, they come up with different representation. For example, this convolutional layer acts as a ear detector, for example. And as we go through the architecture of the network, this data becomes more detailed. The beautiful thing about CNN and why they are so popular and powerful is all of these basically happen automatically. So we don't tell the CNN to, hey, go and find the shape of a cat ear, or go and find, for example, how dogs' eyes look like, or the color of their eyes. The CNN does that automatically just by looking at the samples of image samples of cats and dogs that we supplied. Another common supervised deep neural network is called recurrent neural nets. For the previous two networks, they only look at the observations in one point of time. They are incapable of looking back, looking at the sequence of data and sequence of observations in order to make a prediction for the future.
So what they see is one point of a time only.
There are some situations that in order to learn something, we do need to basically look at what happens in the past. In this case, we have a sequence. That means we want to recognize a sequence.
For example, if you want to predict what would be the value of tomorrow's and a specific stock, you can't only rely on today's observation. You can't only rely what is the value of the stock today. You need to look at a history of the stock values in the past few weeks or even few months in order to have a good prediction for tomorrow.
As I said, the previous neural networks that I just discussed can't do that, but recurrent neural networks are designed to basically learn this type of sequence learning. What you see in this photo is a sample of recurrent neural networks called long short-term memory module, or in short, LSTM. And they are one of the most popular supervised learning algorithms to process sequential data. What they do is they introduce the concept of memory. So they have introduced a concept of short-term memory and long-term memory, and they have built in something like valves that they can basically decide how much of the previous knowledge should be included in the prediction of the data. Their implementation is slightly more complicated, and the reason for that is in addition to the data that we need, the dimension of the data that we have, for example, in a typical RGB image, we have three-dimensional image plus another dimension is the number of the samples that we have. We also need to include another dimension of our data, which is time. We also need to process our data. If our data is not sequential, we also need to do advanced pre-processing to present that data in a sequential format based on the time steps that we want to basically apply.
Likewise, the training is slightly more resource demanding because the your data magnifies. You also need to include all of the time steps that you require to present your data. For example, in our previous stock example, if you want to look at the let's say 60 days of history, each your observations become 60 times larger than a non-sequential platform, which means your network requires to process
a lot more data. It requires more powerful computers, and it's slightly more difficult to basically understand how it works because its architecture is slightly more complex. Also, in addition to these standard type of deep nets that I just explained, it's quite common that we combine these different type of neural network or different type of layers. For example, you can have a neural network that the top layers are, for example, convolutional layers, and then they're followed by recurrent neural networks, for example, LSTM, and then they come and then they have dense neural networks, etc. The whole concept of deep learning is to basically being able to assemble these different layers of neurons of any kind. For example, here we have an example of captioning a video. A video is basically a sequence of images. So our input to the neural network is basically image. That means our top layer that directly receives the input must be convolutional layers. Of course, we can feed it to dense as well, but then we lose all those feature representations or intelligent feature representations that ConvNets apply to images. At the same time, because now we are dealing with a sequence of data, we need to include recurrent neural networks, for example, LST and layers. And you can see that as the input to this video, the label or the caption to this the video is a boy is playing golf. Now, what can we do with deep learning? We have achieved near human level image classification, speech recognition. That means computers can see and hear almost as good as humans. Transcription of handwriting, autonomous driving, much improved translation, machine translation, text to speech. So basically, thanks to neural networks, computers today can see, hear, and talk. We have also enabled a set of new products called digital assistant, leveraging from text to speech and speech recognition, and also natural language understanding, etc. What deep learning cannot do yet? Look at this email. Suppose that you want to design an AI software solution that can reply to customer emails. And then it receives this email. My order arrived a week late, so I wasn't able to give it to my kid as her birthday gift. Can I return it? What we can do is to automatically classify this email. So we can actually create an AI solution that reads this email, classify it as a refund request, and send it to the right department or individual or staff for processing and replying to the client. What the DL cannot do is to form a human-like reply to this message. A reply like, oh, sorry to hear that. I hope your daughter had a good birthday. So what AI cannot do is to compose this message as well as we do. And one reason is because it can't get read this basically email and then associate that kid to her means daughter. That level of intelligence is still not in deep learning. So we can't have near human dialogue systems. Although a few years back, Google demoed a system called Google Duplex that seemed to have a breakthrough in dialogue systems, but so far we haven't seen much from that research or that system in practice, actually. We can have near human machine translation across not very common languages, or human level natural language understanding, as I just showed you in the previous email, in the previous example. We should not take seriously any talk of human level artificial general intelligence. I'll play a video from Professor Andrew Ng, which is one of the pioneers in deep learning right now, to talk about this artificial general intelligence briefly.
There is a lot of excitement, but also a lot of unnecessary hype about AI. One of the reasons for this is because AI is actually two separate ideas. Almost all the progress we are seeing in AI today is artificial narrow intelligence. These are AIs that do one thing, such as a smart speaker or self-driving car, or AI to do web search, or AI applications in farming or in a factory. These types of AI are one-trick ponies, but when you find the appropriate trick, this can be incredibly valuable. Unfortunately, AI also refers to a second concept of AGI, or artificial general intelligence. That is the goal, to build AI that can do anything a human can do, or maybe even be super intelligent and do even more things than any human can. I'm seeing tons of progress in ANI, artificial narrow intelligence, and almost no progress toward AGI, or artificial general intelligence. Both of these are worthy goals, and unfortunately, the rapid progress in ANI, which is incredibly valuable, that has caused people to conclude that there's a lot of progress in AI, which is true, but that has caused people to falsely think that there might be a lot of progress in AGI as well, which is leading to some irrational fears about evil killer robots coming over to take over humanity anytime now. I think AGI is an exciting goal for researchers to work on, but it'll take multiple technological breakthroughs before we get there, and it may be decades or hundreds of years or even thousands of years away. Given how far away AGI is, I think there is no need to unduly worry about it.
One of the major challenges that we currently have in AI is the concept of understanding and intelligence is very limited. With humans, we see, we hear, but what we see and what we hear has meaning. So intelligence for human is not the fact that we see things, it's not the fact that we hear things. Intelligence is how we process and what meanings they have for us as humans. With computers and with AI, we are in a stage that they can see and they can hear, but they don't understand what they see and what they hear. So that's one of the major issues that we currently have with the concept of artificial intelligence, that basically questions then what is intelligence actually reflect in the term artificial intelligence. Nevertheless, this is very important to have to manage the expectation of artificial intelligence. Artificial intelligence is not a new thing. It has been basically a topic that people have been researching and studying for the past 70 or even more years. However, because of the expectations were quite high, we have so far experienced two faults of artificial intelligence. We have to be very careful to set the expectations right, to understand what we can do with AI. So as researchers and engineers, we don't overpromise that result in basically losing support and interest and investment in artificial intelligence in the future. Now, what do you need to start in deep learning? First, you need a proper programming background, some understanding of math, familiarity with the overall machine learning pipeline that you can learn quickly, a computer with NVIDIA GPUs, or if you don't have that, you can use cloud platforms like Google Colab, although what you can do with those free platforms are limited. You can train deep net algorithms on a typical computer without NVIDIA GPU as well, but as long as the data that it needs to process and the depth of the model is not very complex. And obviously a willing to learn. The common programming language for deep learning and machine learning is Python. R is also very popular. You can also do MATLAB. And nowadays we can see that most big organizations like Apple and Google, they also started including libraries to train and create machine learning models. However, for deep learning, especially if you want to design the models yourself instead of using a pre-trained model, you need to mostly code them in Python. Then you can deploy them into different programming languages like Java, etc. Good understanding of data processing packages and NumPy and Pandas on top of them. The IDEs that you can use, the most popular ones are Jupyter Notebook and Spider, also VS Code and etc. And the deep learning packages, the most famous for on TensorFlow One class, Caffe, PyTorch, and Theano. Although not new, The recent advances in machine learning and computing have enabled deep neural nets to be so powerful. We're just in the beginning of deep learning era, and most of their potentials are yet to be identified and explored. Many organizations are using deep nets in their products to provide us with more services and better experience, including healthcare products and services, smartphones, manufacturing, automation, and robotics. If you watch this lecture in 10 years from its recording date, maybe deep learning has evolved and we refer to them with different terms. Or maybe they enabled us to design completely new ways of doing AI. But today, they are the future of artificial and machine intelligence. I hope this lecture answered some of the questions that you had, and you know more about deep learning than an hour ago. If you're interested, there are countless of resources and courses that you can consider to build deep nets. A simple Google search would be a very good start. I'm Dr. Reza Shahamiri, and this was an introductory lecture to deep learning. Goodbye.